Okay, so in this question we've got a car that's broken down at the side of the road. We've got a tow truck that's come to pick them up and tow them home. There's a rope connecting the two, and the maximum load on that rope is 6 kilonewtons or 6,000 newtons. We know a couple of other things. We know the mass of the car, and we know the coefficient of friction between the car and the road. Now the question is in two parts. Calculate the maximum acceleration without breaking the tow rope. So this thing has got to pull this car from rest up to I don't know, normal speed to take it home going down the road, and whilst it's accelerating, this is the limiting factor, because if the force required to accelerate the car becomes more than 6,000 newtons, then the tow rope breaks and everyone has a bad day. So how do we go about this? What shall we do first? Well, first of all, we'll have a little bit of a diagram and we'll try and think about the forces that are acting just on my car. So I know in this scenario for part A, I have got a force coming this way of 6 kilonewtons, which is the maximum tension in my tow rope, and I'm going to call that force Ft for tension. Now I've got two other things that this force must overcome. One of them is quite straightforward. One of them is a force that's acting against the tow rope and the tow truck, and that's going to be friction. So I will need to overcome my friction force in order to move my car along. And the other one is a little bit less obvious, but it's dependent on Newton's laws. If I imagine this is the direction of my acceleration, that's the direction that I'm going to be going in. Now, according to Newton's laws, that implies that there's some sort of force going on. If you remember, F equals ma, and the existence of that acceleration going in that direction implies that there's a force associated with it that is equal and opposite that particular force. So in order to accelerate anything, F equals ma, so there needs to be a force in this direction. F equals ma. And that force there would actually form part of this tension force. So this tension force is overcoming friction, and it's also supplying sufficient force to accelerate this thing. So we know there's a force going in this direction to do this, and that also means there's an equal and opposite force going in the opposite direction, which is why here we've got our force that's causing the acceleration that I'll call Fa. Bit weird? Maybe so, but that's how to think about it. You can think about it in a different way as well if you want to. Instead of the Newton's laws part of it, you can think of the tension in the rope going this way has got to overcome and accelerate this car. So it needs to supply this car with some force in order to accelerate it, and it needs to supply this car also with some force in order to overcome the friction as well. So once you get to that stage, that's the tricky bit really. The rest of it's quite straightforward, because then you can say that everything going in this direction must equal everything going in this direction. So the force that's causing the acceleration and the force that's caused by the friction is going to be equal to the force, the tension force in the rope. And that's the key thing really that you need to come to. I'll put a little margin to actually explain the bits that we do know now. So if I've got my force that's causing the acceleration, I know that's F equals ma, and I know that the force of friction is going to be the normal force that's acting down on my car multiplied by the coefficient of friction. So I've got mu in this case, which is my coefficient of friction, and the weight of my car acting straight down, which will be the normal force, is going to be m times g. And I know that Ft is just Ft, that's the force that the van's supplying for me. So these numbers here I know some of, I don't know others. What I'm trying to actually work out is that one. So we could stick those letters in here and then rearrange to make A the subject of that equation. So Fa equals ma, so I can say there that ma plus mu mg is going to equal to Ft, the tension in my tow rope, and I'm trying to get this thing here to isolate that one. So the first thing I'm going to do is isolate the term that the A is in. So I've got MA. I'm going to take mu mg from both sides. Ft minus mu mg. And the next stage is to isolate A on its own. I've got to divide both sides by mass. So that leaves me with A equals Ft minus mu mg. Remember to do all that first, so I'll stick it in some brackets, and then I'm going to divide that again by the mass. You can simplify that slightly, but I'm not going to bother because that's as much as we need to do. Next stage is to find out from the question what these things are. So I know that the value, the numerical value of Ft will be the maximum value, which is 6,000 newtons, 6 kilonewtons. I know that mu from my question is 0.15. I know that m from my question, both m's in fact, are going to be the mass of the car, which is 1,200 kilograms. So that's just newtons, kilograms, weird values for mu. What else do I need to know? Oh, g, which is 9.81. Generally we used for g. And you substitute these numbers into this formula and you get A equals boom. Okay, I've not done that. It'll take me a few minutes. Now the next part is state the tension when travelling at constant velocity. Now the clue in this part of the question, I suppose, is it uses the word state. Not calculate, but state. So you'd think it would be obvious. So that's the end of part A. This is part A, and this is part B. It seems to think it's obvious. So let's have a think what goes off. When travelling at constant velocity, according again to Newton's laws, something will keep on going in a straight line without speeding up or slowing down or a state of rest or whatever you like, unless a force acts upon it. Now, if you're travelling at constant velocity, there is no force acting on that car. But hang on, it doesn't necessarily mean there's no force acting. It means that the net force, the sum of all the forces, is going to be zero. So there's still going to be tension in the tow rope because you still need to overcome the force of friction when you're towing the car. So although you're not accelerating anything anymore, so there's not this component of force will have disappeared because there's no acceleration going off, you've still got this one. So assuming that this thing stays constant with velocity, which in reality it probably doesn't, but in this question we assume that it does, then this force will equal the force in the tow rope when the net force on the car is zero. So when this is going at constant velocity, this one balances this one, so there's actually no net force on the car. So no acceleration or change in velocity takes place. So the answer for part B is the state of tension when travelling at constant velocity. Well, we have the numbers, but it will be FF. And if you want to work that out as a number, it's mu mg. Again, you can put those numbers in there and come out with a numerical answer.